Welcome. In this video, we'll take a look at sections 1.4 and 1.5, introducing some identities. So we have a chart here of a lot of identities we've looked at so far, including the reciprocal identities, the common equivalent form of those identities, representing the sine, cosine, and tangent functions. We have some of the ratio identities that include the tangent function and the cotangent function. A couple new identities that we can look at are the Pythagorean theorem identities. One of those representations is that cosine theta plus sine theta, or cosine squared theta plus sine squared theta equals 1. We can rearrange this by dividing that initial Pythagorean theorem identity by either a cosine squared or a sine squared to get two other representations of that Pythagorean theorem. So each of those three are going to be useful for working with proving identities in the future and just rearranging our terms in trigonometric equations when we get to those as well. Another thing to review here is, again, the properties of our sine, cosine, and tangent functions. So if we call a angle theta, in reference to that angle theta, our sine of theta will be the opposite side divided by the hypotenuse. Cosine is the adjacent divided by the hypotenuse, and then the tangent function gives us the opposite divided by the adjacent. So all in reference to the input angle. Again, sine, cosine, and tangent all give ratios of right triangles, the sides of those right triangles back. Another little piece of notation is, again, that squared notation. When we write a sine squared theta, in shorthand, we can say that that is the same thing as sine of theta quantity squared. So both of these are actually saying the same thing. So if we consider a example for this, the sine of theta is equal to 3 over 5. We can find the sine squared theta here by just squaring the result of sine. So this would give us 9 over 25. Another thing to note is another way to kind of represent that an angle terminates in a given quadrant. We could say that angle theta ends or is in the quadrant 2, Q2. So this would say that the angle terminates in quadrant 2. Let's take a look at just a little bit of a proof, and it's very short, of our Pythagorean theorem identity. Cosine squared theta plus sine squared theta equals 1. So one thing we can represent first is our angle theta in standard position, where its opposite side is y, adjacent side is x, and the hypotenuse is r. We've seen this picture before, and we know just for the sides of that right triangle that the Pythagorean theorem from algebra has to apply. So x squared plus y squared equals r squared. So we have that from our normal Pythagorean theorem. If I consider dividing the whole equation by r squared, so we divide each term by r squared, we'll get this second line, x squared over r squared plus y squared over r squared equals 1. But we, again, can kind of distribute that squared out or factor that squared out to get x over r squared plus y over r squared equals 1. But these are the definitions of sine and cosine. The cosine ratio is x over r, that's the adjacent over the hypotenuse, and the y over r is the definition for sine. So we can get the cosine squared of theta plus the sine squared of theta is equal to 1. And that is how we get the trigonometric identity for the Pythagorean theorem. So let's take a look at a few more right triangle problems working with finding all of our trigonometric functions for a given angle. So let's start with our tangent of theta is equal to 3 over 4 and terminates in the first quadrant. We want to find the other 5 trigonometric functions. So let's first start by drawing a picture. If I can draw a picture, I can get a good idea of what this angle is looking like. This is an angle terminating in the first quadrant. And its tangent is 3 over 4, so that would be the opposite over the adjacent side. If we recognize these side lengths 3 and 4, we can know that our hypotenuse here is going to be equal to 5. This is a 3, 4, 5 triangle. And now we can go out and solve for the rest of our 5 trig functions, starting with the sine. Sine of theta we can represent as the opposite over the hypotenuse. Cosine, adjacent over hypotenuse. And then the tangent, we already know, so we can write that down on our board. 3 over 4. And now we can get to work with the reciprocal functions. So the reciprocal functions, cosecant, secant, and then finally the cotangent function, which will be 4 over 3. So we have all 6 trigonometric functions here with that given tangent and first quadrant. We can take a look at a second problem like this. We're given the sine function and the cosine function here, and we'd like to go out and solve for the rest of the trigonometric functions. So here, if I'm given the sine and the cosine to start with, one way I can go about this is just using my ratios. I know that the tangent of theta is equal to the sine over the cosine. So I could go and just take the ratio of these 2 trig functions to find this tangent. So we would have negative 20 over 29 divide 21 over 29. We can flip and multiply to get a product. And our tangent function will be negative 20 over 21. Now that we have these 3 trig functions already, I'm just going to find their reciprocals. So the cosecant theta is going to be the reciprocal of the sine function. So that would be negative 29 over 20. The secant function will be the reciprocal of the cosine, which is 29 over 20. 1. And then finally the cotangent function, cotangent theta, will be the reciprocal of the tangent that we just solved for, which is going to be negative 21 over 20. So we found all of the remaining 4 trigonometric functions knowing the sine and the cosine function using some identities. In the next video, we will take a look at some more identities and how they work in terms of their algebra. Thanks for watching.